this becomes 0. Then you get the root. If you just solve this equation, then you get x equals plus or minus root. Okay, that's a solution to this equation. You know that. Okay, so let's see if we can find the root. Let me just write this like this. Remove all of this. We're trying to find the root of x squared minus 2. Okay. And remember, my Newton iterate simply requires me to compute the function value and its derivative. So let's compute the derivative as well. So you know that f prime of x is 2x. Okay. And from here, you simply get the iterate. Xk plus 1 is xk minus the function value at k, which is xk squared minus 2, divided by the derivative at that particular point. So that's 2xk. Okay. So this is simply this function. This is simply the root. And that is the Newton iterate that we've just discussed. Okay. So of course I have to do this for k equals 0, 1, and so on. And my hope is that we'll converge to the solution. Right. So let's say you start at x0 equals 2. Let me get the values. I'm not going to compute these. So at x0 equals 2, you have, so you can remember, you can compute the error. So how far you are from the solution. So if x0 equals 2, that's 2 squared, that is 4 minus 2. So in this particular case, the error is simply, well, I'm going to define, so let's say ek is essentially xk minus root 2. Okay, so in this particular case, what is xk? Xk is 0. Root 2 is roughly 1.41. So in this particular case, this is the error, 0.59. Okay, that's 2 minus 1.41. Okay, so I'm going to plug x0 equals 0 into this equation, and I will get x1 equals 1.5. So if you plug 2, this becomes 2 minus 4 minus 2 divided by 2. Okay, that's 2 divided by 4. So this becomes half. So this is 2 minus half, and that value becomes 1.5. Okay, and the error here is 0.086. Okay, now plug this back in again. You get x2 is equal to 1.4167, and the error is 0.0025. Okay, x3 is 1.414157. Okay, E3 is 2.1 times 2.1 times 10 to the power of minus 6. Okay. Now the thing I want you to note is this is roughly 0.35 times E2. Okay. Now remember what I said. I'm sorry. This is 0.35 times E2 square. It's quadratic convergence. You can plug in those numbers. You'll see 0.35 times E2 square. Now remember, in my on about a minute back, I told you that the constant c is the derivative at xk divided by 2 times f prime of xk. Okay, actually I should be a little more careful. This was the point eta. Okay. Remember, in about a minute back, I told you that the constant, when you divide ek plus 1 divided by ek square, that approaches the second derivative at a point taken between ek and the true solution divided by 2 times the derivative at the kth point. Okay. Now, as you get sufficiently close to the solution, I argued that all of these will start to look like this, x star. Okay. Now, you know what the solution is here. Now, if you just put x star equals root 2, that's the value that we're trying to find out. This is exactly equal to 1 over 2 root 2. Okay. And this value is in fact 0.3536. Okay, and you will notice that this is very, very close to this. Okay, so in fact you're starting to see that the convergence rate starts to become very quadratic as you get close to the solution, and that the constant actually starts to get very close to the second derivative evaluated the solution divided by 2 times the first derivative evaluated at the solution as well. Okay, so there are a few more notes I want to make here. If you were to start this iteration at x equals 0, you will notice that the iterative method actually fails. If you start this at x0 greater than 0, and if you just run this iteration, as we have seen here, this will converge to x star equals root 2, which is the solution we were looking for. And if you actually run this iteration from x star is less than 0, this converges to x star equals minus root 2, which is kind of cool. You got all of the roots of the equation that you wanted. Okay, so this is what I wanted to cover on Newton's iterate. Please make sure you understand the Newton iterate. Please make sure you understand the convergence rate and the constant on the convergence rate. And please make sure that you're actually able to apply this in the context of specific functions that might be given to you. Thank you.